326 years. That is how long one section of the San Andreas Fault has been completely, utterly disturbingly quiet. No major rupture, no release, just pressure. Building silently, like a held breath that has lasted longer than the United States has existed. And right now, something directly south of that silence just woke up very loudly. 400 earthquakes in 48 hours. The rate is accelerating, the magnitudes are climbing, and scientists have identified 3 specific criteria that separate a routine swarm from something far more serious. 2 of them are already checked. Stay with me, because the third one is where this gets very interesting, and the next 72 hours will either check that box or close this case permanently. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. The line that just got crossed. Something just changed. Not in a way that made the news cycle, not in a way that sent emergency alerts to your phone or put a breaking banner across your television screen. It changed quietly, the way the most dangerous things always do. In the data, in the numbers, in the slow accumulation of signals that individually mean nothing, but together mean something that scientists who study this region have been watching for with a specific kind of disciplined dread. Let me tell you exactly what happened. In the span of 48 hours, the Brawley Seismic Zone, a stretch of Southern California that sits at one of the most geologically complicated intersections on the North American continent, produced roughly 400 earthquakes. 400 in 2 days. And before you tell yourself that California gets earthquakes all the time, which it does, and that this is probably nothing, which it might be, I want you to sit with the rate for a moment, because the rate is the signal that matters here. This swarm did not arrive at 400 events on day 1. It accelerated. The rate climbed from 22 events per hour during the early phase to 33 events per hour at peak. That is not a swarm maintaining itself. That is a swarm that is picking up speed. And when something that is releasing energy starts releasing it faster, the question seismologists ask is not, when will this stop? It is, what is driving the acceleration? Then there is the magnitude picture, because a swarm of 400 tiny earthquakes is one thing. What has been happening with the size of these events is something else entirely. The magnitude floor, meaning the threshold below which most events are clustering, has been rising. In the first 24 hours, the swarm was dominated by events below magnitude 4.5. That is significant seismic activity, but it sits within what researchers consider the normal operational range of the Brawley Zone. Then, within a single 24-hour window, the ceiling cracked. The 2 largest events in the sequence came in at approximately magnitude 4.66 and magnitude 4.7. Those numbers may look modest on paper, but context transforms them. Context is everything in seismology. These were not shallow, superficial events rattling around in the top few kilometers of crust, where fluid pressure and geothermal noise can generate misleading signals. These ruptures occurred at depths between 13 and 16 kilometers. That puts them squarely in what geologists call the brittle crust, the cold, rigid portion of the lithosphere where rocks do not bend, do not flow, and do not accommodate stress gradually. They lock, and then they break. The fact that these earthquakes are occurring at that depth tells you something fundamental. This is not surface noise. This is the architecture of the crust failing under load. Now, the people who watch this zone most closely, the researchers and observers who have been tracking the Brawley Seismic Zone across multiple swarm sequences going back decades, have laid out a specific diagnostic framework. 3 criteria, each of which, if met, escalates the interpretation of this event from routine to something that demands a different kind of attention. The first criterion is event count growth. That box is checked. Roughly 400 earthquakes in 48 hours at an accelerating rate satisfies that threshold. The second criterion is magnitude increase. That box is also checked. The progression from a sub 4.5 floor to a magnitude 4.7 ceiling in under 24 hours satisfies that threshold. The third criterion, and this is the one that will define everything over the next 72 hours, is northward migration, and that box remains open. Here is why that matters so much. Here is why the third criterion is not just another data point in a list of 3. It is the entire question. The Brawley Seismic Zone does not exist in isolation. It sits at the southern end of a fault system whose northern expression is one of the most studied, most feared, and most consequential geological structures in the world. The behaviour of a swarm in this zone, specifically its direction of movement, can tell you whether you are watching a system that is releasing stress locally, burning through accumulated energy in a contained burst, or whether you're watching the first chapter of a stress transfer event that could reach something far larger and far more dangerous. Migration is the diagnostic. Migration is the test. And as of right now, the test is still running. This is not a prediction. I want to be absolutely clear about that, because clarity matters when the subject is earthquakes, and the audience is people who live in Southern California, or know people who do. This is not a prediction. It is an observational framework. Scientists are not saying an earthquake is coming. They are saying that this swarm has crossed 2 out of 3 thresholds that have historically been associated with stress transfer events, and that the next 72 hours will either confirm or dismiss the concern. So here is the question we are actually asking. Is this a contained swarm, a system burning through locally stored stress, one that will peak, decay, and be added to the historical catalogue as another Brawley sequence? Or is this the first step in a process of stress moving northward, toward the southern San Andreas Fault, toward a section of that fault that has not ruptured in 326 years? That question does not have an answer yet, but by the time this window closes, it will. And the answer, whatever it turns out to be, will tell us something critical about the current state of one of the most hazardous fault systems on Earth. Part 2. Geometry is Destiny. You cannot understand what is happening in the Brawley Seismic Zone without understanding where it sits, because location in geology is not just geography, it is destiny. The specific position of this zone relative to the fault surrounding it is what transforms a regional swarm into a potentially consequential event. In earthquake science, geometry is fate. The Brawley Seismic Zone occupies a narrow corridor between 2 major fault systems. To the west and south, the Imperial Fault runs through the Imperial Valley in a roughly northwest-southeast orientation. To the north, the southern terminus of the San Andreas Fault anchors what seismologists call the Coachella Section, a locked and loaded stretch of one of the most hazardous fault segments in the continental United States. The Brawley Zone is the connective tissue between these 2 systems. It is not a single clean fault. It is a distributed mesh of fractures, a zone of deformation where the 2 larger systems interact, overlap and hand stress back and forth like partners in a relay race. This is why fault junctions amplify uncertainty in a way that a single isolated fault does not. On a single fault, stress accumulates in a relatively predictable fashion along a well-defined plane. You can model it, you can estimate slip rates, you can build recurrence intervals with reasonable confidence. At a junction, where multiple faults converge, where the geometry is messy, where stress is being partitioned among several potential rupture surfaces simultaneously, the system has degrees of freedom that make prediction dramatically harder. Any one of several faults can absorb the next increment of stress. Any one of them can slip first. The junction is where the model gets complicated and where the data matters most. What makes the Brawley Zone specifically interesting, and specifically alarming in the context of this swarm, is that it functions as a stress transfer corridor. That is the concept that sits at the centre of why this particular swarm is being watched so carefully. A stress transfer corridor is not a passive feature of the geology. It is an active mechanism, a pathway through which energy loaded onto one part of the fault system can migrate into another. Think of it as a transmission system. The stress does not stay where it originates. It can travel, it can redistribute. And when it moves through a corridor like the Brawley Zone, the direction it moves matters enormously. Seismologists use the phrase rupture handoff to describe a scenario where a seismic sequence on one fault segment triggers activity on an adjacent or connected segment. This does not require a single continuous rupture. The faults do not need to be directly touching. What is required is that the stress released by one event, or a sequence of events, changes the loading conditions on a neighbouring fault, nudging it closer to its failure threshold. When that happens, you have not just one earthquake or one swarm, you have a cascade, a chain of mechanical influence propagating through the crust, along the path of least resistance, or more accurately, along the path of greatest susceptibility. The Brawley Zone measures approximately 58 kilometers in active length. This is not a small feature. It is not a local anomaly. It is a fault zone whose total extent covers a significant portion of the gap between the Imperial Fault to the south and the San Andreas proper to the north. And critically, within this 58-kilometre zone, the current swarm is not distributed evenly. It is not a single uniform cluster of activity spreading smoothly across the whole system. Instead, seismological data shows two distinct clusters of events, separated by a gap, a stretch of relative quiet running through the middle of the active zone. That gap is one of the most interesting features in the current dataset. Two competing interpretations present themselves, and they lead to radically different conclusions. The first interpretation is that the gap represents a structural barrier, a region of the crust that is either not under sufficient stress to produce events, or that is geometrically isolated from the main rupture surfaces generating the swarm. If this is the case, the gap may act as a natural firebreak, limiting the northward extent of stress transfer and confining the swarm to its current footprint. The second interpretation is considerably less comfortable. The gap may represent a locked segment, a portion of the fault that is accumulating stress faster than it is releasing it, a reservoir of elastic energy that has not yet found expression in seismicity, but that is nonetheless being loaded by the activity on either side of it. In that scenario, the quiet is not absence of stress. It is the silence of a coiled spring. And there is a third possibility, which is that the gap is a stress shadow, a region temporarily shielded from failure by the geometry of recent ruptures on adjacent segments, whose stress state will normalize as the surrounding seismicity evolves. Each of these interpretations implies a different trajectory for this swarm. Each implies a different answer to the central question we're tracking. What this geometry ultimately tells us is that the direction of swarm migration is not just a curiosity. It is not a secondary detail. It is the primary diagnostic signal in this entire event. If activity remains confined to the southern cluster, if the gap persists, if there is no northward propagation of seismicity toward the San Andreas, then the geometry has contained the stress locally. But if events begin to appear north of the gap, if the swarm begins migrating in the direction of the Coachella Section, then the corridor is open, stress is moving, and it is moving toward the one segment of the southern San Andreas that has been loaded without release for longer than any recorded cycle. This is the one place on Earth right now where a swarm can either dissipate harmlessly into the geological record or connect with something that has been waiting under pressure for 3 centuries. Part 3. The 326-year silence problem. Let me put a number in front of you and ask you to really hold it. 326 years. That is how long it has been since the Coachella section of the southern San Andreas Fault last ruptured. The year was approximately 1690 to 1700. William III was on the English throne. Isaac Newton had published the Principia less than 15 years earlier. The entirety of the American colonial period, the Revolution, the Civil War, the Industrial Revolution, 2 world wars, the nuclear age, the space age, all of it has unfolded while this single section of the San Andreas Fault has sat locked, building stress, accumulating what seismologists call slip deficit, waiting for the day when the accumulated elastic energy in the crust exceeds the frictional resistance holding the fault closed. That day has not come yet, but the waiting has been going on longer than it should have. Here is the context that makes that number genuinely alarming rather than just impressively large. The mean recurrence interval for the Coachella section, the average time between major ruptures, calculated from geological evidence preserved in fault trenches, lake sediments, and the offset features of the landscape, is approximately 180 years, give or take 60. Even at the far upper end of that range, adding 60 years to 180 gives you 240 years before the Coachella section has exceeded its expected quiet period. The current gap is 326 years. The Coachella section has been silent for nearly a century longer than the most generous estimate of its normal recurrence interval. This is what geologists mean when they refer to a fault being overdue. The term carries a specific technical meaning that is easy to misread. Saying a fault is overdue does not mean an earthquake is certain or imminent. Faults are not operating on a schedule. They do not know what year it is. They respond to stress, not to calendars. But overdue does mean that the expected elastic energy release cycle has run longer than historical norms without completing, which implies with genuine physical meaning, not just statistical hand-waving, that more strain energy has accumulated in the rocks than was present at the start of the previous cycle. The longer the silence extends past the mean recurrence interval, the larger the slip deficit becomes. Slip deficit is the concept that translates time into danger. The Coachella Section sits in a zone where the Pacific and North American plates are moving relative to each other at a rate of approximately 20 to 35 millimeters per year, depending on the specific fault segment. On a creeping fault, a segment where a seismic slip allows the plates to move gradually without building dangerous levels of elastic strain, that plate motion is accommodated continuously and relatively harmlessly. But the Coachella Section is not a creeping fault. It is a locked fault. The two sides of the fault are stuck together, held in place by friction while the deep roots of the plates continue to shear past each other. The strain is not being released. It is being stored, invisibly, in the elastic deformation of the rocks on either side of the fault plane. 326 years of locking at 20 to 35 millimeters of relative plate motion per year. Work through that arithmetic and you arrive at somewhere between 6.5 and nearly 12 meters of accumulated slip deficit. That is the distance the fault wants to move but has not been allowed to. When it does move, not if, when, that energy will be released in a matter of seconds, and the magnitude of the resulting earthquake will be directly proportional to the accumulated strain. The USGS estimates a significant probability of a major rupture on this section within a 30-year window. This is not fringe science. This is the consensus hazard assessment from the agency responsible for characterizing seismic risk in the United States. It is also worth noting what did not happen in 1857. The Fort Taillon earthquake of January 9, 1857, was one of the largest historical earthquakes in North America, a colossal rupture of the San Andreas Fault that tore approximately 350 kilometers of the fault from Parkfield in the northwest to the Cajun Pass area in the southeast. It was a catastrophic event that shook the entire region, with a magnitude estimated between 7.7 and 7.9. And it did not rupture the Coachella Section. The rupture stopped before reaching it. The Coachella Section remained locked through one of the most powerful San Andreas events ever recorded, absorbing the stress changes from a nearby giant without releasing its own accumulated energy. It has remained locked ever since. So when we talk about the current Brawley swarm and ask whether stress could transfer northward into the Coachella Section, we are not asking whether stress would find a fault there that has never been tested. We are asking whether a swarm in the transfer corridor immediately to the south could deliver an additional increment of Coulomb stress, the kind of mechanical nudge that can push a fault from stable to unstable, to a segment that has already been accumulating energy for longer than any measured cycle. Stress has been building in that section for 326 years. If even a fraction of what is being released in the Brawley zone right now finds a pathway north, it does not arrive at an empty system. It arrives at a system that may already be very, very close to its own breaking point. Part 4. The magnitude signal. People are missing. A magnitude 4.7 earthquake is, by most everyday definitions, a moderate event. It shakes things, it startles people, it rattles dishes and wakes up pets, and gets mentioned on the local news before the segment cuts to weather. In the context of global seismicity, which generates thousands of earthquakes per day across all magnitude ranges, a 4.7 is ordinary, unremarkable even. So when I tell you that the magnitude 4.7 event in this swarm is one of the most significant signals in the current dataset, I want to explain exactly why. Because the significance is not in the number itself, it is in what the number represents about the trajectory of this system. The concept you need here is magnitude ceiling creep. In a seismic swarm, the distribution of event sizes follows a statistical pattern described by something called the Gutenberg-Richter relationship, a mathematical model that predicts, for any given threshold magnitude, how many earthquakes of that size or larger you should expect. Under normal swarm conditions, the ceiling, the largest magnitude you observe, tends to be set early and stays relatively constant as the swarm evolves. The swarm produces its biggest event, and subsequent activity clusters below that level. What has been happening in the Brawley zone over the past 48 hours is different. The ceiling has been moving upward. The swarm did not open with its biggest event. It has been producing progressively larger events as it accelerates. That is the pattern of a system under increasing stress, not a system releasing stress and winding down. There is also the concept of a rising floor, not just the ceiling, but the minimum magnitude of events that are occurring at significant frequency has been shifting. Early in the sequence, the majority of events were well below magnitude 4. As the swarm has evolved, the energy scale of the whole distribution has shifted upward. Larger events are becoming more common, not just occasional. The statistical center of gravity of the swarm is climbing. In physics terms, the system is not bleeding off energy in a smooth, gradual dissipation curve. It is escalating. Something is feeding it, and whatever is feeding it has not yet reached its equilibrium. Now, let me put this in historical context, because the Brawley Seismic Zone is not a place without a seismic history. The zone has produced notable swarms in 1981, 2012, and 2020, among others. Each of those sequences had its own character, its own magnitude profile, its own duration and spatial pattern. The current swarm, in its event count and rate metrics, is behaving within the broad envelope of past Brawley activity. It is not doing something so wildly unprecedented that there are no comparisons to draw, but its magnitude trajectory is trending toward the upper portion of that historical range. It has not exceeded the envelope, but it is approaching the ceiling of what past Brawley swarms have produced, and it is doing so while still accelerating. The next threshold that seismologists are watching is magnitude 5.0. This is not an arbitrary round number. A magnitude 5 event represents a qualitative change in the energy budget of the system. Earthquake magnitude is measured on a logarithmic scale. Each full unit of magnitude represents roughly 32 times more energy released than the unit below it. The jump from 4.7 to 5.0 is not large in terms of the numbers, but in terms of the physical energy involved, it is substantial. A magnitude 5 earthquake in this zone would represent a significant increase in the mechanical perturbation being delivered to the surrounding fault system. And in the specific geometry of the Brawley Zone, where the surrounding fault system includes both the Imperial Fault and the southern San Andreas, a magnitude 5 event could meaningfully alter the stress state on both. Here is what I want you to take away from this. When observers watch a swarm for signs of escalation, they are not waiting for a single dramatic moment. They are watching a ladder. The escalation ladder is a concept where each rung represents a threshold, in magnitude, in rate, in spatial extent, and crossing any one of those thresholds does not trigger an alarm by itself. But crossing multiple rungs on multiple dimensions simultaneously is a different signal entirely. The current swarm has already crossed rungs on the rate ladder and the magnitude ladder. The question is whether it also crosses the spatial ladder, whether the events migrate northward and add directional stress transfer to the package of signals that are already demanding attention. Magnitude is not the signal alone. Direction plus magnitude combined with rate in this specific geological location, that is the signal. And right now, 2 of the 3 components of that signal are already lit. Part 5. The real-time clock starts now. The third criterion, the one that remains unresolved, the one that the 72-hour window is designed to test, is northward migration. And before we talk about what migration in this context would mean, I want to make sure we are talking about the same thing, because the word gets used loosely, and in seismology, it carries a very specific meaning. In a seismic swarm, spatial migration refers to the systematic movement of the centroid of seismic activity, the statistical center of where earthquakes are occurring, in a particular direction over time, not random scatter, not events appearing throughout the whole zone simultaneously, which can happen in a distributed stress field and does not imply directional propagation. Genuine migration is directional, progressive, and mechanically meaningful. It tells you that something is moving through the crust, either fluid pressure propagating along a permeable fault zone or a seismic front driven by elastic stress transfer from a nucleating rupture, or the progressive failure of a fault segment as stress is redistributed from event to event. Different mechanisms, different physical implications, but all of them directional, all of them observable if you are watching the data in real time. The expected pathway for northward migration in this zone runs from the current cluster of activity toward the Salton Sea and then toward Bombay Beach, the small community on the northeastern shore of the Salton Sea that sits essentially on top of the mapped trace of the southern San Andreas Fault. This is not an arbitrary geographic direction. It is the structural direction dictated by the fault geometry of the Brawley Zone and the orientation of the regional stress field. If stress is being transferred from the active swarm clusters toward the San Andreas, the physical pathway it follows is northward through the connector zone, toward the Salton Sea, toward the locked fault at its northern margin. A seismic front, once it begins propagating, tends to move at a rate that is observable over hours to days. It is not instantaneous. The leading edge of the migrating activity should appear as new events clustering progressively further north than previous events, creating a spatial pattern in the data that is distinct from the random scatter of a stationary swarm. This is what seismologists and monitoring systems will be watching for over the next 72 hours. The data resolution available to California's seismic monitoring networks, one of the densest and most sensitive in the world, is sufficient to detect this kind of propagation in near real time. If it is happening, we will know relatively quickly. Why 72 hours specifically? It is not a magic number. It is a practical diagnostic window based on how stress transfer events have historically evolved in this and similar fault zones. When migration occurs in a swarm context and represents genuine stress propagation toward an adjacent fault system, the propagation front typically becomes apparent within the first few days of swarm acceleration. If you're at the 48-hour mark, as we are right now, and migration has not yet become clearly evident in the spatial data, the next 24 hours will either reveal the trend or fail to produce it. Swarms that are going to transfer stress generally show that behavior early. Swarms that are going to decay generally begin showing the statistical signatures of decay, decreasing event rate, stabilizing magnitude ceiling, spatial contraction, within this same window. The 72 hours is not a deadline after which nothing can happen. It is a window during which the swarm will communicate its nature. If migration materializes, if events begin appearing systematically north of the current cluster boundary, tracking toward the Salton Sea, leaving a spatial trail in the data that points toward the Coachella Section, then the interpretation of this swarm shifts from routine Brawley activity to active stress transfer event. That does not mean an earthquake is imminent on the San Andreas. It means that the most concerning of the three possible scenarios we are tracking has moved from theoretical to observationally supported. The probability of a foreshock type sequence increases. The attention of the seismological community intensifies. The monitoring posture of every agency responsible for earthquake preparedness in Southern California goes up a level. And if migration does not materialize, if the swarm continues to evolve without showing directional propagation, without crossing the boundary of the gap separating the two clusters, without producing new events tracking northward toward the San Andreas, then by the time this window closes, we have a contained Brawley swarm, significant, scientifically interesting, another data point in the historical record of this seismically hyperactive zone, but not the opening act of something larger. By the time this 72-hour window closes, this swarm will have told us what it is. The clock started 48 hours ago. It is still running. Part 6. This is not a fault, it's a machine. To understand why the Brawley Seismic Zone produces swarms the way it does, why it is prone to these bursts of accelerating clustered activity that have now crossed our diagnostic thresholds, you have to understand the geological environment it inhabits, because it is one of the most unusual tectonic settings in North America. This is not your standard California fault zone. This is a pull-apart basin sitting at the collision point of two incompatible styles of plate motion, and the result is a geological system that is almost engineered to produce exactly the kind of seismic behavior we are currently witnessing. The Brawley Zone sits within the Salton Trough, a low-lying basin that runs from the Gulf of California in the south to the area around the Salton Sea in the north. The trough is the northernmost expression of a spreading center, a zone where the crust is being pulled apart, where new material is being injected from below to fill the gap created by extensional tectonics. This is the same kind of process that creates ocean basins, but here it is happening on land, which is relatively rare. The Gulf of California to the south is an early-stage ocean. The Salton Trough is even earlier stage, a continental rift that has not quite separated the Baja California Peninsula from the mainland of Mexico, but is actively trying to. At the same time, the region is dominated by the right lateral strike-slip motion of the San Andreas Fault system, where the Pacific Plate is moving northwestward relative to the North American Plate. These two tectonic regimes, spreading center extension pulling the crust apart east-west, and strike-slip shear driving northwest-southeast motion, interact in the Salton Trough, to create what geologists call a transtensional environment. The crust here is simultaneously being sheared and pulled apart. The result is a complex network of faults oriented in multiple directions, accommodating this multi-directional deformation in a distributed fashion across the whole zone rather than concentrating it on a single clean rupture plane. This is exactly why the Brawley Seismic Zone exists as a zone rather than as a single fault. The distributed deformation of a pull-apart basin expresses itself through swarms, through diffuse seismicity, through clusters of smaller events spread across a broad area, because the stress is being accommodated by many fault segments acting simultaneously rather than by one master fault building toward a single large rupture. The zone is, in a very real physical sense, designed to do what it is doing right now. It is designed to produce exactly these kinds of swarms. Swarms are normal here. Historically, the Brawley Zone has produced swarms in 1981, 1993, 2005, 2012, 2020, and at multiple other times when the data is less complete. The frequency of swarm activity is itself a feature of the tectonic environment. The geothermal activity in the region, the elevated temperatures, the presence of fluids in the crust. All of these factors lower the threshold for fault slip, allowing stress to be released in these distributed bursts rather than building to catastrophic levels on a single locked plane. In this sense, swarm activity in the Brawley Zone is not a symptom of danger. It is in most cases a pressure release mechanism, a way the system bleeds off stress before it becomes overwhelming. But here is the tension that makes the current situation different from a routine Brawley swarm. The stress relief function of the Brawley Zone only works as advertised when the swarm stays local. When the energy dissipates within the zone itself and does not migrate into the adjacent locked fault segments to the north and south. The system is designed to release stress in bursts, yes, but the direction and extent of that release determines whether the burst is a safety valve or a trigger, and that is precisely why the northward migration criterion is the test that matters. A Brawley swarm that stays in the Brawley Zone is the system working as designed. A Brawley swarm that sends stress northward toward the Coachella Section is the system becoming something different, a coupling mechanism between a distributed release zone and a locked, loaded and very patient fault that has been waiting for exactly this kind of perturbation. Part 7. The heat beneath it. There is something else living under the Brawley Zone that deserves a mention, not because it changes the fundamental interpretation of this swarm, but because it adds a layer of geological context that explains a great deal about the region's behaviour. The Salton Sea geothermal field is one of the most thermally active areas in the continental United States. The geothermal gradient, the rate at which temperature increases with depth, in this region runs at approximately 200 degrees Celsius per kilometre. That is extraordinary. For comparison, the global average geothermal gradient is roughly 25 to 30 degrees Celsius per kilometre. The Salton Trough is running roughly 8 times hotter than typical crust. This extreme thermal environment has two primary effects on seismic behaviour. First, it lowers the brittle ductile transition depth, the depth at which rock behaviour shifts from brittle fracture to ductile flow. In a normal continental crust, this transition occurs at roughly 15 to 20 kilometres depth. In the Salton Trough, the elevated temperatures push that transition shallower, meaning that the zone of the crust capable of producing earthquakes in the classic sense is compressed. Most of the seismic activity in the region, including the current swarm, occurs within this relatively shallow seismogenic zone, which is consistent with the 13 to 16 kilometre depths we observed in the larger events. Second, and crucially for interpreting the current swarm, the elevated geothermal gradient also means elevated fluid activity within the crust. Hot, pressurized fluids can migrate along fault zones, temporarily reducing the effective normal stress on fault planes and triggering slip. Fluid-driven swarms are a recognized category of seismic sequence, and they tend to have distinctive characteristics: gradual migration, moderate maximum magnitudes, and a lack of clear main shock-aftershock structure. Some observers have raised the question of whether fluid involvement could be contributing to the current Brawley activity. It is a legitimate hypothesis. However, importantly, there are no volcanic inflation signals in the region, no anomalous gas emissions, and no other geochemical indicators that would suggest a major fluid injection event is driving the swarm. The behaviour of the current sequence, particularly its accelerating rate and its rising magnitude ceiling, more closely resembles tectonic stress release than fluid-driven seismicity. The heat is real, the fluids are present, but the signal points towards stress transfer, not thermal plumbing, and that keeps us squarely focused on what matters most. Which direction is this stress heading? Part 8. The volcanic ghost layer. The geology of the Salton Trough has one more character worth introducing briefly, because understanding what this region is not doing right now requires knowing what it has done before. At the northern end of the Salton Sea, a cluster of low hills called the Salton Buttes represents one of the youngest volcanic features in California. These rhyolite domes last erupted approximately 1,800 years ago, not in geological time, but in actual calendar time. 1,800 years before the present, which means they were active while the Roman Empire still existed. In the geological timescale, that is practically this morning. The presence of young volcanic features in the immediate vicinity of the Brawley Seismic Zone is a fact that occasionally generates alarm when seismic swarms occur, and it is worth addressing directly. Volcanic eruptions are commonly preceded by seismic swarms, because magma moving through the crust fractures rock and triggers earthquakes along the pathways of intrusion. If this swarm were volcanic in origin, we would expect to see specific indicators: ground deformation measurable by GPS and INSAR satellite data, harmonic tremor signals in the seismograms, anomalous gas ratios at surface monitoring sites, and temperature changes in the geothermal fluids of the region. None of these signals are present. There is no current evidence of magmatic intrusion contributing to the Brawley swarm. The volcanic history of the Salton Buttes is real and worth knowing, but it is not part of today's story. Today's story is tectonic. It is about stress moving through locked rock, not magma moving through conduits, and that keeps the central question precisely where we left it. Not whether the volcano is waking up, but whether the stress in the Brawley zone is moving north. Part 9. The B-value debate. There is a number hiding inside this swarm's data that seismologists find extremely interesting, and also deeply frustrating, because it hints at something significant while stubbornly refusing to confirm it. That number is the B-value, and understanding what it means, and what it cannot tell us, is essential for calibrating our interpretation of the current sequence. The B-value is derived from the Gutenberg-Richter relationship, that statistical law describing how earthquakes of different magnitudes are distributed within any given seismic catalogue. Specifically, the B-value is the slope of the line you get when you plot the logarithm of the number of earthquakes against their magnitude. A higher B-value means your catalogue is dominated by smaller events relative to larger ones. Lots of tiny earthquakes, few large ones. A lower B-value means the distribution is weighted toward larger events relative to smaller ones. Your big earthquakes are more common than a standard distribution would predict. In typical tectonic settings, the B-value clusters around 1.0. When B-values drop significantly below 1, when they approach values like 0.7 or 0.8, the seismological community interprets this as a potential indicator of elevated differential stress. The physical argument is relatively intuitive. In a high-stress environment, the rock has less capacity to release energy in small increments, so a greater proportion of the total energy release occurs in larger events. A low B-value, under this interpretation, suggests that the fault system is under unusual load. It is the geological equivalent of a boiler gauge reading high. For the current Brawley swarm, early analysis suggests a B-value below 1.0. This is consistent with the magnitude ceiling creep and rising floor we discussed earlier, and it fits within the pattern of an elevated stress interpretation. If you were constructing a case that this swarm represents something more than routine energy release, if you were building the argument that the Brawley zone is currently under unusual load relative to its historical baseline, the B-value is a piece of supporting evidence. But here is where honest science demands a pause. The B-value is notoriously sensitive to catalogue completeness and dataset size. You need a large, complete catalogue of well-recorded earthquakes to estimate B-value reliably. Small datasets, like the catalogue accumulated over 48 hours of a swarm sequence, generate highly uncertain B-value estimates. The statistical error bars around a B-value calculated from a few hundred events are large enough that a true value of 1.0 cannot be excluded, even if your point estimate is 0.8. Seismologists who are careful about this, which is most of them, treat a sub-1 B value in an early swarm as a hint, not a conclusion. So the B-value in the context of this swarm is doing what good scientific data often does. It is adding weight to a hypothesis without confirming it. It is consistent with elevated stress. It is consistent with a system that has been loaded beyond its normal operating range. It is consistent with the interpretation that this swarm is occurring in a fault zone that is closer to its failure threshold than usual, but it is not by itself dispositive. It is a piece in a puzzle, and the puzzle only resolves when all the pieces align. What the B-value cannot tell us, and this is the crucial limitation, is anything about direction. It cannot tell us whether the stress responsible for the low B-value is going to migrate northward. It cannot tell us whether the Coachella section is the recipient of whatever elevated stress this swarm reflects. For those questions, we are back to the third criterion. We are back to migration. We are always back to migration. The B-value is a hint. Northward migration is the conclusion, and that conclusion is still being written in real time. Part 10. The two-cluster problem. One of the most puzzling and potentially most significant features of this swarm is something you would only see if you plotted all 400 events spatially, mapped them out on the surface as a geographic distribution, rather than treating them as an abstract count. When you do that, a structure emerges that is not immediately obvious from the event rate or magnitude data alone. The swarm is not a single continuous cluster. It is two clusters, separated by a gap. The northern cluster and the southern cluster of the current swarm are each internally coherent, tight groupings of events that suggest active rupture on specific fault segments within the zone. Between them, there is a stretch of the Brawley zone where event density drops significantly. Not to zero, necessarily, but noticeably lower than in the active clusters. This gap runs roughly through the middle of the active sequence, and its existence raises a series of questions that currently have more candidate answers than confirmed ones. The first possibility is that the gap represents a fault segmentation boundary, a structural discontinuity in the fault geometry that physically separates the northern and southern parts of the zone. Many fault systems are not continuous from end to end. They are composed of segments separated by step-overs, bends, or other geometric complexities, and these segmentation boundaries often control how far a rupture can propagate. If the gap in the current swarm corresponds to a real segmentation boundary in the fault, it may be acting as a rupture barrier, a feature that prevents seismic energy from transmitting across the gap from one cluster to the other. If this is correct, it is actually good news for the stress transfer hypothesis. The barrier limits northward propagation, keeping the swarm contained. The second possibility is considerably more troubling. The gap could represent a locked patch, a portion of the fault that is under high normal stress, strongly coupled and not currently slipping in small increments. A locked patch in the middle of an active swarm zone would be accumulating stress from both directions simultaneously. Events on its southern flank load it from below, events on its northern flank load it from above. If this is what the gap represents, then the quiet in the middle is not safety. It is the silence of something under increasing load that has not yet found its breaking point. A locked patch in this position, surrounded by active seismicity, is exactly the kind of feature that can suddenly rupture as a discrete, larger magnitude event, potentially producing the magnitude 5 or above event that would represent the next rung on the escalation ladder. The third possibility brings us back to the concept of a stress shadow. Earthquakes do not just release stress, they also redistribute it. The slip on a fault plane during a rupture increases stress in some areas and decreases it in others, creating zones of elevated and reduced failure probability around the rupture. A stress shadow is a zone of reduced failure probability created by a recent rupture nearby. The gap could be a region temporarily shielded from seismicity, not because it is structurally different, but because recent events have pushed its stress state away from failure. This would be a temporary condition that normalizes over time, and it carries its own implications for how the swarm will evolve. Each of these interpretations carries a different implication for northward migration. If the gap is a barrier, it may stop propagation. If it is a locked patch, it is a potential site for a larger event that could drive stress north more abruptly than the gradual migration of a swarm front. If it is a stress shadow, it will resolve over time, and the two clusters may eventually merge or transmit across the quiet zone. What matters for the central question, the question of whether stress reaches the Coachella section, is whether the northern cluster, whichever way it evolves, finds a pathway past the gap and continues migrating toward the San Andreas Fault terminus. Is that gap stopping something, or is it loading something? In 72 hours, we will have significantly more data to work with. But right now, the most honest answer is, we do not know. And that uncertainty, sitting at the geometric centre of an already complex system, is precisely what makes this swarm so difficult to read and so important to watch. Part 11. The solar flare coincidence. Here is where the story gets interesting in a different way. At roughly the same time that the Brawley swarm was entering its acceleration phase, as the rate was climbing from 22 to 33 events per hour and the magnitude ceiling was pushing past 4.5, the Sun produced a significant event of its own. An M-class 5.7 solar flare erupted from the solar surface, accompanied by a coronal mass ejection and a significant radio burst. The timing overlap between a major solar event and an accelerating seismic swarm on one of the world's most closely watched fault systems is the kind of coincidence that the internet notices immediately, and it did. Within hours, the discussion had spread widely. Was the solar activity connected to the earthquake swarm? Was the same energy that drives space weather somehow also influencing the rocks beneath Southern California? It is a compelling narrative. The Sun and the Earth, linked in a cosmic cause and effect chain, with the Brawley swarm as Exhibit A. And I understand why it captures the imagination, because the timing is striking. But here is where I have to be precise rather than dramatic, because the data tells a story that is less cinematic and more rigorous. The mechanism most commonly proposed for a solar seismic link involves geomagnetic activity, the idea that a strong coronal mass ejection, by disturbing Earth's magnetic field, could induce electrical currents in the crust that alter the stress state on faults or change the fluid pressure in fault zones, triggering seismicity. It is a physically plausible sounding hypothesis. The problem is the data. The geomagnetic indices, the Cape index, the DST index, the measures that quantify actual disturbance of Earth's magnetic field, were low during the period of peak swarm acceleration. The coronal mass ejection had not yet reached Earth and interacted with the magnetosphere by the time the swarm was already running at its peak rate. There was no geomagnetic storm in progress during the critical window. The Earth's magnetic field was, by all measurements, relatively quiet. And beyond the timing problem, there is the energy problem. The magnetic field perturbations associated with even the most powerful geomagnetic storms deliver energy to the crust that is orders of magnitude smaller than the energy required to trigger fault slip on the scale we are observing. Researchers who have looked at this question systematically, examining large earthquake catalogues against solar activity records, have found correlations that are weak at best and statistically marginal in all but a handful of studies that have faced significant methodological criticism. The scientific consensus, which is not unanimous but is overwhelming, is that there is no robust causal mechanism connecting solar activity to earthquake triggering at the scale of events in this swarm. What we can say about the solar flare is that it happened. Its timing with the swarm is a coincidence worth noting because it is the kind of coincidence that drives misinformation cycles, and the best way to inoculate against misinformation is to address it directly with data. But the swarm must be evaluated on its own seismological merits, on the rate, the magnitude, the depth, the spatial distribution, and above all, the direction of migration. Those are the signals that will determine what this event becomes. The Sun, in this particular story, is a spectacular bystander. Part 12. The energetic convergence narrative. Online, the solar flare did not exist alone. It was immediately incorporated into a broader narrative that has been circulating in earthquake-adjacent communities for years, a theory that I will call the energetic convergence framework. The argument goes roughly like this. When multiple energetic systems, solar flares, deep focus earthquakes in remote regions, volcanic unrest at multiple locations and surface seismic swarms all align within a short time window, it represents a meaningful convergence of planetary scale forces, and the result is elevated risk of a major earthquake or other catastrophic event. I want to engage with this seriously rather than dismissing it, because the people who believe it are often genuinely paying attention to the world's geophysical data, which is more than most people do. The instinct to look for connections between large-scale energetic events is not irrational. In science, we're always looking for connections, and many of the most important discoveries came from noticing correlations that seemed improbable. until a mechanism was found that explained them. The problem with the energetic convergence framework is not the instinct. It is the mechanism, or rather the absence of one. The energetic systems being grouped together in this narrative are separated by distances ranging from tens of thousands of kilometers for distant deep focus earthquakes to 150 million kilometers for the Sun. The Earth is not a single unified resonating body that transmits energy coherently across these distances. It is a layered, geologically complex system in which energy dissipates rapidly with distance through multiple forms of absorption and scattering. A magnitude 7 subduction earthquake in Tonga does not deliver meaningful mechanical energy to a fault zone in Southern California. A coronal mass ejection interacting with Earth's magnetosphere does not deliver meaningful stress changes to brittle crust, 13 kilometers below the Imperial Valley. The energy budget simply does not work. The pattern recognition that makes the convergence narrative feel compelling is a feature of human cognition, not a feature of physical reality. We are exceptionally good at finding patterns in data, and we're also exceptionally prone to finding patterns that are not actually there, to seeing signal in noise when multiple independent random events happen to cluster in time. The probability of multiple energetic events occurring within a short window across different systems that are each independently active most of the time is higher than intuition suggests. They do not need a common cause. They need only the cognitive tendency to notice them together and construct a narrative that connects them. What determines whether this swarm is a foreshock, a stress concentration event, or a routine Brawley sequence is not how many other things are happening on Earth or in the solar system this week. It is whether the swarm migrates northward. One criterion, one direction, one test, not global alignment, not solar concordance, just the behavior of earthquakes in a 58-kilometer fault zone over the next 72 hours. Part 13. The Global Seismic Backdrop. While the Brawley swarm has been accelerating, the broader global seismic record has been active in a way that has contributed to the convergence narrative I just described. Events in Tonga, Papua New Guinea, Japan, and the Solomon Islands have all generated significant seismicity in recent days, prompting observations that global earthquake activity seems elevated. This impression is worth addressing briefly, because it shapes how non-scientists are interpreting the Brawley swarm. The Earth generates somewhere between 12,000 and 14,000 earthquakes of magnitude 2 or above per year, distributed unevenly across the planet's tectonic boundaries. In any given 2-week window, it is statistically expected that multiple regions along the Pacific Ring of Fire, which includes Tonga, Papua New Guinea, Japan, and the Solomon Islands, will produce significant seismic events. These events are not connected to each other in any physical sense that would be relevant to the Brawley swarm. They are independent expressions of independent tectonic systems, each operating on its own stress accumulation and release cycle. Clustering in global seismicity happens routinely and regularly, without implying a common cause or a coordinated systemic shift. The Brawley swarm is not significant because global seismicity is elevated. The Brawley swarm is significant because of its specific location, its specific geometry, its specific behavior, and its specific relationship to the Coachella section of the San Andreas Fault. Those local factors, not the global backdrop, are what make the diagnostic window of the next 72 hours meaningful. Part 14. The Deep Focus Fiji Cluster. Among the global events that have attracted attention in connection with the Brawley swarm, a cluster of deep focus earthquakes in the Fiji region stands out for the wrong reason, which is to say, it has been cited as a possible connection, and that connection does not hold up to scrutiny, but is worth understanding precisely so you can see why it does not hold. Deep focus earthquakes, defined as events occurring below 300 kilometers depth, occur in subducting slabs, the sheets of dense oceanic crust that are diving beneath overriding plates in subduction zones. These events can occur at depths exceeding 600 kilometers, which puts them in the transition zone between the upper and lower mantle. A cluster of over 500 deep focus events in the Fiji region, occurring at depths greater than 500 kilometers, is scientifically interesting and worth studying for what it reveals about slab dynamics in the Tonga-Kermadec subduction system. It is not, however, physically connected to surface seismicity in Southern California in any way that would be mechanically meaningful. The stress changes generated by a deep focus earthquake are largely contained within the subducting slab itself. They do not propagate as coherent stress waves through 10,000 kilometers of mantle and crust to arrive intact at a fault zone in the Imperial Valley. The seismic waves propagate, yes. Seismometers around the world record deep focus events from Fiji. But seismic waves passing through the crust are not the same as stress changes accumulating on fault planes. One is a transient vibration, the other is a permanent change in the mechanical loading of a fault. The Fiji Deep Focus Cluster is a passing reference, not a signal. The Brawley Swarm migrating northward would be a signal. These are not the same story. Part 15. The Haida-Gwaii Anomaly. There is one genuinely unresolved data anomaly from this period that deserves more careful treatment than the others, and it comes from a very different corner of the Pacific. Haida-Gwaii, the archipelago off the northern coast of British Columbia. During the period when the Brawley Swarm was accelerating, a tsunami alert was issued for the Haida-Gwaii region without a clearly identified causative earthquake. The alert was generated, monitoring systems registered something, and yet the seismic record did not contain an obvious large event that should have triggered it. The alert was subsequently resolved without a tsunami making landfall, and the standard explanations offered included data lag in the processing systems, a possible instrument anomaly, and the chance that a submarine landslide, which can generate tsunamis without producing significant seismic signals, had occurred. What makes this interesting is not that it implies a connection to the Brawley Swarm. It almost certainly does not. Haida-Gwaii and the Imperial Valley are separated by thousands of kilometers and entirely different tectonic regimes. What makes it interesting is that it is a reminder that our monitoring systems, as sophisticated as they are fallible. Data anomalies, instrument errors, and incomplete seismic catalogues are part of the reality of operating global monitoring networks. The same networks that will tell us whether the Brawley Swarm is migrating northward are the networks that briefly produced an unresolved tsunami alert in a different ocean basin. They're very good. They're not perfect. This matters for how we interpret the 72-hour window. The signal we're watching for, directional northward migration in the Brawley seismic data, is real and detectable. California's seismic monitoring infrastructure is among the best in the world. But the Haida-Gwaii anomaly is a useful reminder to hold all monitoring data with appropriate epistemic humility. We are watching real-time data from complex systems managed by fallible instruments. When the window closes and the data makes a case, that case will be strong, but it will not be perfect, and the decisive signal, whatever shape it takes, will remain the behaviour of the Brawley Swarm itself, not anything happening in British Columbia or Fiji or on the surface of the Sun. Part 16, Scenario 1. The Swarm dies quietly. Let me walk you through the most probable future first, not because it is the most dramatic, but because accuracy demands that we begin with the base rate. In a field where the most consequential events are also the rarest, there is a persistent gravitational pull toward the tail of the distribution, toward the scenarios that are most alarming, most vivid, most worth writing about. Resisting that pull is not pessimism about the science, it is fidelity to it. The base rate exists for a reason, and the base rate here is not ambiguous. The most common outcome for seismic swarms in the Brawley Seismic Zone, across the entire historical catalogue of sequences in this region, looking at 1981, 1993, 2005, 2012, 2020, and the more fragmentary earlier records that predate dense instrumentation but are recoverable from regional catalogues, is relatively benign. The swarm peaks. The event rate, which has been climbing toward 33 events per hour, stabilizes and then begins to decline, first gradually and then more steeply, tracing the kind of decay curve that Amori's law has described for over a century. The magnitude ceiling, which has been creeping upward toward 4.7, does not cross the next threshold. No events appear north of the current cluster boundary. The gap between the two clusters, the spatial discontinuity in the hypercenter distribution that represents either a genuine barrier in the fault geometry or simply an unloaded section that the current stress driving has not reached, persists. It does not fill in. It does not become a migration corridor. The spatial footprint of the swarm does not expand northward in the way that a stress transfer event would require, and over a period of days to a week or two, the seismicity gradually subsides, leaving behind a slightly enriched seismic catalogue and a region that is, if anything, marginally less stressed than it was before the swarm began. That last point deserves emphasis because it runs counter to the intuition that more earthquakes means more danger. The distributed release of energy across 400 small events does represent a real, if modest, reduction in local stress. The crust has done mechanical work. Strain has been converted to slip across many small fault patches. The stress field in the immediate vicinity of the swarm has been partially reorganized in ways that may actually reduce the short-term probability of a larger event in that specific volume of crust. This is not a general rule that applies in all directions and all distances. Coulomb stress transfer can simultaneously relieve stress in some orientations while loading it in others. But within the swarm footprint itself, the quiet death of a sequence is a genuine stress release event, not simply an absence of catastrophe. In retrospect, and this is where the concept of retrospective bias becomes essential to understand, this outcome looks obvious. When a swarm dies quietly, the narrative writes itself almost automatically as it was just another Brawley swarm. The criteria that were unmet, the migration that never appeared, the magnitude threshold that was never crossed. These absences become the story, and the story is simple and clean and deeply unsatisfying to anyone who was paying attention during the window. Not this time. Not a foreshock sequence. Not a stress transfer event. Not the beginning of a cascade that ended somewhere on the Coachella section of the San Andreas. Just a routine expression of the Brawley Zone doing what the Brawley Zone does, which is to say, producing swarms, cycling through periods of elevated activity, and returning to background seismicity without triggering the larger system. But here is the thing about retrospective bias, and why I want you to understand it clearly before this window closes and the retrospective interpretation begins. When this swarm ends quietly, and there is a meaningful probability that it will, a probability that has been the base rate throughout this analysis, there will be people who look back at the attention paid to it and conclude that the attention was disproportionate, that the concern was overblown, that scientists and observers who watched this sequence carefully were catastrophizing a routine event, pattern matching noise into signal, seeing threat in what was always just background geology expressing itself in familiar ways. This conclusion would be wrong, and it would be wrong in a way that has practical consequences for how the next sequence is interpreted and communicated. The attention was appropriate because the two criteria that were met, count growth and magnitude increase, are genuine signals that demand investigation. They are not noise. They are not the product of overactive pattern recognition. They are the specific quantitative thresholds that the seismological framework for evaluating swarm sequences identifies as meaningful, and they were met here in a way that was unambiguous. The fact that the third criterion was not met does not retroactively drain the first two of their significance. They meant what they meant when they were observed. The accelerating rate was real. The rising magnitude ceiling was real. The depths at which the largest events occurred, 13 to 16 kilometers, well into the seismogenic zone, were real. None of that becomes meaningless because the migration did not follow. The framework worked. It identified a potentially significant sequence. It defined a diagnostic window with a specific duration and a specific criterion for resolution. It specified in advance what would confirm the concern and what would dismiss it. And the data answered the question. That is not alarmism being vindicated or debunked. That is science functioning correctly, the way that science is supposed to function, which is to say by making falsifiable predictions and then checking them against observation, rather than by arriving at conclusions and then selecting evidence to support them. The absence of migration, if it occurs, is not a failure of the framework. It is the framework working exactly as designed. A diagnostic test that never returns a positive result is not a useful test. A diagnostic test that returns a positive result when the criteria are met and a negative result when they are not is doing precisely what diagnostic tests are for. And the swarm dying quietly is not a boring outcome. It is an outcome that carries specific recoverable information about the current state of the fault system and the mechanical conditions that govern this particular episode. It tells us specifically one of several things. It tells us that the gap between the clusters functioned as a genuine mechanical barrier, that there is something about the fault geometry or the stress field in that intervening section that prevented the propagation of seismicity northward, and that this barrier held under the stress conditions produced by this swarm. Or it tells us that the stress driving the swarm was locally contained, that the energy budget of this sequence was insufficient to drive propagation beyond its current footprint, and that the system was not sufficiently loaded in the regional sense to turn a local swarm into a corridor event. Or it tells us that the two-cluster geometry we observed was itself a product of fault segmentation that imposes a natural limit on how far swarms in the southern cluster can propagate before encountering a section of the fault network that does not respond to the same driving stress. Each of these inferences is distinguishable, at least in principle, from the others, and each of them updates our understanding of what the Southern Imperial Valley fault system looks like right now, in its current state of loading and partial stress release. All of them contribute to the ongoing project of characterizing what the Southern San Andreas is doing, not in the abstract but concretely in real time, with the data that this swarm produced. There is also a longer perspective worth keeping in view as this window approaches its resolution. Every swarm that the Brawley Zone has produced, every sequence in the catalogue going back to the earliest reliable records, every episode of elevated seismicity that was watched carefully and resolved quietly, has added to the empirical foundation on which the current monitoring framework rests. The base rate that allows us to say, with some confidence, that the most probable outcome is benign, is itself a product of having watched enough sequences end quietly to know what quiet endings look like and how often they occur. The catalogue is not just an archive, it is the instrument, and this swarm, whatever it turns out to be, will become part of that instrument for the researchers who watch the next one. If this is how the next 72 hours resolve, if the rate declines, the ceiling holds, the gap persists, and the Brawley Zone adds another completed sequence to its long history of completed sequences, we add a data point to the catalogue, we update our understanding of the current stress geometry in the Southern Imperial Valley, and we acknowledge, without embarrassment and without the false conclusion that the watching was wasted, that the most common outcome was once again the one that occurred. The framework held, the question was answered, the answer was the expected one, and then we keep watching. Because the Coachella Section is still there, north of the gap, still locked, still loading, still accumulating the strain that 326 years of tectonic motion has deposited along its length. The quiet death of this swarm does not change that arithmetic. It only means that this was not the sequence that resolved it. The next one might be, or the one after that. The watching does not stop because this window closed without incident. It continues because the fault continues, indifferent to our relief, building toward the question that has not yet been asked. Part 17, Scenario 2, Stress Without Release. The second scenario is the one that gets the least attention in popular discussions of earthquake risk, probably because it is the hardest to dramatize and the hardest to observe directly. There is no dramatic moment, no headline event, no seismogram trace that spikes off the chart and gives everyone a clear before and after. It does not involve a main shock. It does not involve a damaging earthquake at all, at least not on any timescale that is immediately observable. And yet, and I want you to stay with me here because this is the part that genuinely unsettles the scientists who think about it most carefully, it may be the most consequential scenario of the three in terms of what it implies for long-term hazard in the region. The quiet scenario is sometimes the dangerous one. This is the scenario in which the Brawley swarm represents a symptom of regional stress concentration, rather than a direct precursor to a rupture on the San Andreas. The distinction sounds subtle at first, like a technicality, like the kind of fine-grained academic difference that matters to researchers, but not to anyone living in the Imperial Valley, or the Coachella Valley, or Los Angeles. But it carries a very different set of implications for how we monitor the fault, for what signals we prioritize, and for how we think about the current hazard state of the Southern San Andreas. The difference between a precursor and a symptom is the difference between a spark and a pressure gauge. One implies timing, the other implies loading, and loading, sustained over time, is how the really big earthquakes eventually happen. Here is the conceptual model you need to understand this scenario fully. The crust of Southern California is not a static object that only moves when earthquakes happen. It is not a rigid shelf that sits quietly between events, waiting to be disrupted. It is a dynamic system under continuous load from the relative motion of the Pacific and North American plates, two of the largest tectonic plates on Earth, moving past each other at roughly 50 to 60 millimeters per year in total, distributing that motion across a network of faults that spans hundreds of kilometers in width. Stress is constantly accumulating on faults throughout the region, not just on the San Andreas, and the pattern of that accumulation is influenced by the three-dimensional geometry of the fault network, the mechanical properties of the crust at different depths and temperatures, and the entire history of past earthquakes going back thousands of years. Every rupture that has ever occurred in this region left behind a permanent change in the stress field. The crust remembers, in a mechanical sense, everything that has ever happened to it. When a cluster of seismicity like the current Brawley swarm occurs, 400 events in 48 hours slip distributed across multiple fault segments within a 58-kilometer zone. It does not just release stress locally and leave the surrounding region unchanged, it changes the stress field, not just locally, but regionally. The slip on those Brawley zone faults redistributes elastic strain energy across a broad volume of crust, and the redistribution follows the laws of continuum mechanics in ways that are now well understood, even if the specific numbers for any given event carry significant uncertainty. Some faults, as a result of that redistribution, are brought closer to failure. They receive what is called a positive Coulomb stress change, meaning the stress acting to cause slip on those faults has increased. Other faults are pushed further away from failure. They receive a negative Coulomb stress change, meaning the stress-driving slip has decreased. The pattern depends on the geometry of the faults that slipped, the orientation of the receiving faults, and the direction of the principal stress axes in the regional stress field. It is not random, it is deterministic. We can model it. We just cannot model it with perfect precision, because the inputs carry their own uncertainties. The concept at the center of this scenario is Coulomb stress transfer, and it is the physical mechanism that connects the Brawley swarm to the Coachella section of the southern San Andreas, even if migration does not occur in the seismological data. Even if the 72-hour window closes without a single new event appearing north of the current cluster boundary, even if the swarm dies quietly and never crosses the third diagnostic criterion, the stress transfer still happened. It is physics, it is not optional. Events in the Brawley zone that slip on northwest striking right lateral faults, which is the dominant style of faulting in this region, consistent with the overall San Andreas system kinematics, will tend to transfer Coulomb stress in a pattern that loads fault segments to the north and south along the same structural trend. The Coachella section sits to the north along exactly this structural trend. Its orientation, its sense of motion, and its position relative to the Brawley zone place it squarely in the region of positive Coulomb stress change produced by right lateral slip on northwest striking Brawley faults. This is not a speculative geometric argument. It follows directly from the mathematics of elastic dislocation theory, which has been tested and validated against observed triggered seismicity patterns across dozens of earthquake sequences worldwide. So what this means, concretely, is the following. Even without a visible northward migration of seismicity, even in the scenario where the swarm ends cleanly and the third criterion is never met, the 400 events in this swarm have almost certainly delivered a small but real increment of Coulomb stress to the southern San Andreas Fault. The Coachella section has received a mechanical nudge, not a shove, not the kind of stress change that would push a fault from stable to imminently failing in a single event, but a nudge. And the critical question, the one that cannot be answered by watching the 72-hour window, is how much of a nudge and whether it is enough to matter given the enormous accumulated slip deficit already present on the Coachella section after 326 years of locking. Here is the brutal honesty of this scenario. We do not have a precise answer to that question. Coulomb stress modelling for the current swarm would require a detailed understanding of the geometry of each individual rupture plane among the 400 events, the slip distribution on each of those planes, and the three-dimensional mechanical properties of the crust between the Brawley zone and the Coachella section. Some of those inputs can be estimated from the seismological data. Others carry large uncertainties. The result of such a model would be a Coulomb stress change estimate with error bars wide enough to include both essentially zero effect and measurable loading increment. What we can say with confidence is that the direction of the stress transfer is toward the Coachella section, and the sign of the stress change is positive, meaning it promotes rather than inhibits failure. The magnitude of that change is uncertain. The direction is not. In this scenario, the signal to watch over a longer timescale, not 72 hours but weeks to months after the swarm concludes, is the behaviour of microseismicity on the San Andreas Fault itself, not on the Brawley Zone, which will return to its baseline activity level, not on the Imperial Fault to the south, on the San Andreas, specifically on the Coachella Section. If the Coachella Section begins showing even marginal increases in small earthquake activity in the weeks following the Brawley swarm, events that would individually be too small to feel, too modest to make any news, but statistically significant as a change from the pre-swarm baseline, it could indicate that the Coulomb stress transfer from the Brawley sequence has pushed the fault slightly closer to a state transition, closer to the condition where the accumulated strain energy exceeds the frictional resistance holding the fault locked. This kind of signal is subtle and genuinely easy to miss in a noisy background of routine microseismicity, which is why it requires careful, patient monitoring over time rather than a snapshot assessment of what is happening right now. The stress without release scenario is uncomfortable precisely because it has no clean resolution, no moment where the story ends and the verdict is delivered. The swarm ends, the event rate drops back toward baseline, no major earthquake follows in the days or weeks immediately after, the region appears to calm, the news cycle moves on, and yet the stress state of the Coachella section may be fractionally closer to failure than it was before the swarm began, not dramatically closer, not imminently closer in any way that a monitoring system could detect with current technology, but closer in a real, physical, mechanically meaningful sense, in the way that every small increment of loading on an already overloaded system brings it marginally nearer to the threshold it cannot cross indefinitely. And here is why that matters more in this specific case than it would in almost any other fault system in the country. On a fault operating within its normal recurrence cycle, a fault that ruptured 100 years ago and whose mean recurrence interval is 200 years, a small Coulomb stress increment from a neighbouring swarm is a small perturbation on a system that still has significant remaining capacity. On the Coachella section, which has already exceeded its mean recurrence interval by 86 years, which is already carrying 326 years of accumulated slip deficit, the margin between current loading and failure threshold may be considerably smaller than it would be at any earlier point in the cycle. That is the thing about a fault this far past its expected rupture date. Every additional increment of stress, from distant earthquakes, from neighbouring swarms, from the relentless grinding of the plate boundary itself, lands on a system that has progressively less room left to absorb it. Fractionally closer, on a fault like that, carries a weight it would not carry anywhere else. Part 18, Scenario 3, the foreshock pathway. This is the scenario that nobody wants to say out loud. It is the one that gets discussed in careful, hedged language in scientific papers, the one that emergency managers think about in private meetings, the one that seismologists approach with the particular kind of disciplined caution that comes from knowing exactly how wrong a premature alarm can go, and exactly how catastrophic a missed signal can be. So let me say it plainly, the way it deserves to be said, and then immediately put it in its proper context, because both halves of that sentence matter equally. There is a real possibility, small but real, that the current Brawley swarm is a foreshock sequence, that the 400 events in the last 48 hours, with their accelerating rate and their rising magnitude ceiling, are not the main event. They are the opening act, the first chapter of a sequence whose final chapter is written by a fault that has been under load for 326 years and has not yet had the opportunity to say anything about it. That the third criterion, northward migration toward the Salton Sea and the southern San Andreas, will be met over the next 24 to 48 hours, that stress will propagate from the Brawley zone into the transfer corridor, and that the sequence will culminate in a significant earthquake on a section of fault whose accumulated energy has been building since before the United States existed as a country. I said that plainly. Now let me give you the context that makes it honest, rather than alarmist, because the context is not a footnote. It is essential to understanding what this scenario actually means and how seriously to hold it. The probability that any given seismic swarm sequence is a foreshock sequence, meaning that it is followed by a larger main shock that it preceded in time and space, is, depending on the study, the region, and the methodology used, somewhere between approximately 5 and 10%. Let that sink in for a moment before you run anywhere. 5 to 10%. That means that 19 times out of 20, a swarm is a swarm. It begins, it evolves through its own internal dynamics, it peaks, and it decays. It ends without triggering anything larger. The seismic energy dissipates across hundreds of small ruptures, the stress field adjusts, and the region returns gradually to its background level of activity. The swarm gets filed in the catalogue and studied by graduate students, and the fault that everyone was watching either resumes its silence or continues its normal background seismicity, and nobody writes a headline about it. 19 times out of 20. That is the base rate. And base rates exist for a reason. They encode the accumulated experience of watching thousands of swarm sequences in dozens of tectonic settings around the world. When you're trying to assess any individual sequence, the base rate is where you start. It is the prior probability before you factor in any of the specific characteristics of this particular event. Concern about the foreshock hypothesis should be held lightly, as a possibility that demands monitoring and careful observation, rather than a likelihood that demands immediate preparation for catastrophe. Anyone who tells you otherwise is not reading the science correctly. But, and this is the qualification that every honest treatment of this topic has to include, the Brawley case is not drawn from the general population of seismic swarms. It is not a generic swarm in a generic fault zone somewhere in the middle of a stable tectonic plate. The base rates computed across all global swarm sequences, averaged across everything from mid-plate intraplate seismicity to subduction zone aftershock sequences to geothermal swarms in Iceland, may not apply with full accuracy to what is currently happening between the Imperial Fault and the southern San Andreas Fault in the Salton Trough of Southern California. Context modifies base rates. It always does. And the specific context of the Brawley Zone is, to put it mildly, unusual. The characteristics that make the Brawley Zone relevant to the foreshock hypothesis, in a way that distinguishes it from most swarm environments, are exactly the ones we have been building toward throughout this entire account. First, its location. The Brawley Zone is not adjacent to a fault that is operating within its normal stress cycle. It is adjacent to a fault section, the Coachella Section of the southern San Andreas, that has been locked and loading for 326 years, well beyond its mean recurrence interval of approximately 180 years. A swarm occurring next to a fault operating normally carries a different foreshock probability than a swarm occurring next to a fault that is already carrying 86 years of excess loading beyond its expected rupture date. The proximity to an overdue fault raises the conditional probability above the base rate, even if we cannot quantify by exactly how much. Second, the documented history of this specific zone. The Brawley Seismic Zone has produced swarms throughout the historical and instrumental record, and while most of them resolved without triggering larger events, consistent with the base rate, the broader Salton Trough region has also produced sequences that escalated in ways that were not anticipated in real time. The fault systems here are demonstrably capable of producing large earthquakes, and the geologic record contains evidence of triggered and cascading ruptures in this zone going back centuries. This is not a region where the upper end of the magnitude range can be dismissed as theoretical. Third, and most immediately relevant to the current diagnostic window, the combination of signals already present in this swarm is unusual even within the Brawley historical catalogue. The accelerating rate, 22 to 33 events per hour during peak acceleration, combined with the rising magnitude ceiling and the brittle crust depths of the two largest events, has already crossed 2 of 3 diagnostic thresholds that observers use to distinguish potentially significant sequences from routine background activity. 2 out of 3 is not nothing. It is the system telling you to pay attention, and paying attention is exactly what is happening right now. The historical precedent most directly relevant to the foreshock scenario is one that shook the region not so long ago. On April 4th, 2010, a magnitude 7.2 earthquake struck in northern Baja California, Mexico, the El Mayor Cucapa earthquake, named for the mountain range whose fault system produced the rupture. This was not a small event. It was felt across a broad region of the southwestern United States and northwestern Mexico. It caused significant damage in the Mexicali Valley. It triggered widespread liquefaction and ground deformation throughout the delta region of the Colorado River, and it was preceded by foreshock activity in the broader regional fault system, activity that, at the time it occurred, was not clearly identified as a foreshock sequence. It looked like swarm activity in a seismically active region. The precursory nature of those events was only fully understood in retrospect, after the main shock provided the reference point that defined them as foreshocks. This is the epistemological trap that sits at the centre of the foreshock problem, and it is the most important thing I can tell you about this scenario. Foreshocks do not announce themselves. They carry no label. They arrive in the seismic record dressed identically to the swarms that never produce a main shock, the 19 out of 20 that simply end. The pattern that distinguishes a foreshock sequence from a routine swarm is only visible in retrospect after the main shock has occurred, and you can look back at the preceding seismicity with the advantage of knowing what came next. In real time, looking forward, you have the same data as always. A rate, a magnitude distribution, a spatial pattern, and a set of diagnostic criteria that shift the probability but cannot resolve the uncertainty. The signal that would most strongly support the foreshock interpretation, the observation that would move the needle most significantly in this direction, that would shift the probability assessment from small but real toward elevated and demanding response, is precisely the northward migration that we've been using as the third diagnostic criterion throughout this entire analysis. If, over the next 24 to 48 hours, events begin appearing systematically north of the current cluster boundary, not randomly scattered, but tracking directionally toward the Salton Sea and toward Bombay Beach, where the San Andreas Fault trace runs at the surface, then the foreshock hypothesis gains observational support that it currently lacks. That migration would mean that stress is not staying local. It is propagating. It is moving toward the southern San Andreas along the structural corridor that connects the Brawley Zone to the Coachella Section, and it is doing so in a way that is visible in the seismic data in real time. That would not be proof of an imminent main shock. Nothing in seismology constitutes proof of an imminent main shock, but it would be the strongest signal currently possible that the sequence has stepped beyond the bounds of a locally contained Brawley event and is behaving in a way that is consistent with stress transfer toward an overdue fault. It would mean the monitoring posture of every relevant agency changes. It would mean the scientific conversation changes. It would mean the probability assessment changes, not to certainty, but meaningfully away from the base rate. The most important thing to hold on to as you think about this scenario is the asymmetry of what we can know in real time versus what we can only know in retrospect. Science is watching for every signal that would shift the probability: migration, magnitude escalation, directional propagation, changes in the spatial distribution of events relative to the gap between the two clusters. Those signals are being tracked continuously, but science cannot guarantee that catching those signals early would provide meaningful warning time even if they appear. The geological system operates on its own schedule, in its own units of time, according to its own internal mechanics. It does not negotiate. The best we can do is watch carefully, interpret honestly, communicate clearly, and update our assessment as the data comes in. And the data is coming in right now in real time. Every minute of the next 72 hours adds another data point to a record that will eventually tell us what this swarm was. We just have to be patient enough and honest enough to let the data speak before we decide what it says. Part 19. The escalation ladder. Let me build you a picture of what escalation looks like concretely, because the abstract language of seismic thresholds becomes a lot more meaningful when you attach it to specific physical realities. The ladder has 4 rungs. Each one represents not just a larger number on the magnitude scale, but a qualitatively different physical regime, a different category of mechanical event, a different set of downstream consequences, and a different set of questions that the monitoring community must answer in real time. Rung 1 is where we currently sit. The swarm is producing events in the 4.5 to 4.7 range at an accelerating rate. At this level, the primary concern is the diagnostic picture. Are we watching a contained release or a stress transfer event? There is no significant direct hazard from these events. They are felt by people in the region. They cause no major damage. They represent the system doing exactly what the Brawley Seismic Zone has done throughout its documented history, cycling through episodes of elevated activity and returning eventually to background levels. The question that defines this rung is not one of consequence but of trajectory. The events themselves are manageable. What matters is what they are telling us about the mechanical state of the crust beneath the valley floor, and whether the story they're telling is one of convergence or divergence, a system bleeding off stress in small increments, or a system loading towards something larger. Rung 2 is a magnitude 5 event. As I noted earlier, this is not just a number. It represents a 32-fold increase in the energy released by a single event compared to magnitude 4. That ratio is worth sitting with for a moment, because the logarithmic nature of the magnitude scale has a way of obscuring what are, in physical terms, enormous differences in the mechanical work being done on the crust. A magnitude 5 earthquake in the Brawley Zone would be widely felt across the Imperial Valley, potentially causing minor damage to older structures, particularly unreinforced masonry buildings and older residential construction that has not been retrofitted to modern seismic standards. Agricultural infrastructure, the irrigation systems, the storage facilities, the processing plants that form the economic backbone of the valley, would face elevated risk of minor disruption. More significantly, a magnitude 5 event would represent a meaningful change in the mechanical state of the zone. It would alter the Coulomb stress field in a way that is non-negligible for adjacent fault segments, redistributing stress in patterns that could either stabilize or destabilize neighboring sections of the fault network, depending on the geometry of the rupture. A magnitude 5 event would be the clearest signal yet that the system's energy budget has shifted upward and that the sequence is not converging toward a decay. At Rung 2, the monitoring community shifts from a diagnostic posture to an anticipatory one. The question is no longer only what this swarm means, but what it might be preceding. Rung 3 is a magnitude 6 event, and this is where the language of escalation begins to carry genuine weight. A magnitude 6 begins to represent fault activation in a meaningful sense, a rupture long enough and involving enough slip to potentially trigger sympathetic failure on adjacent segments. The fault patch involved in a magnitude 6 rupture is approximately 10 to 15 kilometers in length. That is not a point source releasing energy quietly into the surrounding crust. That is a surface that has moved, that has shed stress along its own plane and loaded the volumes of rock at its tips, and whose mechanical influence extends outward in all directions through the elastic crust. In the specific geometry of the Brawley Zone, a magnitude 6 event occurring close to the northern cluster boundary could deliver a stress pulse to the southern San Andreas that is large enough to move the probability needle on near-term San Andreas failure. The distances involved are not comfortable buffer zones. They are the kind of distances over which Coulomb stress transfer has been documented to play a role in triggering subsequent events. The historical record in the Imperial Valley provides no reassurance on this point. The Imperial Valley earthquakes of 1940 and 1979, both significant events in the broader region, demonstrated that the fault systems here are capable of producing magnitude 6 and above events with relatively little warning from the surrounding seismicity record. The 1940 Imperial Valley earthquake was magnitude 6.9. The 1979 Imperial Valley earthquake was magnitude 6.4. Both caused significant damage to the agricultural infrastructure of the valley. Both were felt across a wide region extending into Arizona and deep into Baja California. Both occurred in a fault system that had been producing background seismicity of the kind we are watching now, without providing a clear precursory signal that distinguished that particular episode from the many others that did not escalate. The historical record, in other words, does not offer a reliable template for distinguishing swarms that stay at Rung 1 from swarms that climb to Rung 3. That ambiguity is not a failure of the science, it is an honest reflection of how fault systems behave. Rung 4 is the scenario that seismic hazard assessments for Southern California describe in their most carefully worded probabilistic language, a major rupture on the Coachella section of the San Andreas Fault. Magnitude 7 plus, potentially magnitude 7.8 or above, if the rupture propagates beyond the Coachella section into adjacent segments to the north, threading up through the San Bernardino and Mojave sections in a cascade that the fault's geometry does not mechanically prohibit. This is not a scenario triggered directly by the current Brawley swarm in any deterministic sense. The base probability of a Brawley swarm triggering a Coachella section main shock within any given 72-hour window is very low. That probability is worth stating clearly because the public discourse around seismic events has a tendency to collapse probabilistic statements into binary ones. Either it is going to happen, or it is not, and that collapse destroys the most important information the science can actually provide. But the conditions that make such a scenario physically conceivable, the 326-year loading period, the locked fault accumulating slip deficit at roughly 25 millimeters per year, the accumulated elastic strain that has nowhere to go except into eventual rupture, are real, established, and quantified by decades of geodetic measurement and paleoseismic excavation. The Coachella section of the San Andreas is not a theoretical hazard. It is a fault that has ruptured repeatedly through the Holocene, with recurrence intervals that the current inter-event period has already exceeded. The escalation ladder does not end at rung 3, it extends to rung 4, and while the probability of climbing that high from the current situation is low, the consequences of arriving there would be measured not in cracked foundations and broken windows, but in the reshaping of one of the most densely populated and economically critical regions of the United States. The infrastructure exposure alone, water conveyance systems, transportation corridors, energy transmission networks, the built environment of communities that have grown up in the fault's shadow, represents a damage potential that emergency planners have spent decades modelling and that no model has fully captured. Each rung on this ladder requires a different kind of response from the monitoring community. At rung 1, the response is observational and interpretive, dense instrumentation, continuous waveform analysis, rapid relocation of hypercenters, assessment of the migration criterion. At rung 2, the response becomes communicative. The public needs to understand that the energy scale has shifted, that minor damage is possible, that the system is behaving in a way that warrants attention. At rung 3, the response becomes operational. Emergency management agencies activate. Mutual aid frameworks are tested. Probabilistic statements about rung 4 are updated and issued with the kind of transparency that allows downstream decision makers to act. At rung 4, the response is no longer a seismological problem. It becomes a civilizational one. Each rung also carries a different set of cascading implications for the fault system itself, not merely for the human communities sitting above it. Faults are not passive conduits for releasing pre-existing stress. They are dynamic systems that interact with one another through the elastic crust, and an event at rung 2 changes the stress environment that governs the probability of an event at rung 3. The ladder is not a static classification scheme. It is a description of a physical process that, once set in motion, moves according to its own mechanical logic. The current swarm sitting at rung 1.5, with its accelerating rate, its rising magnitude ceiling, and its unresolved migration criterion, is the early chapter of a story whose subsequent chapters have not been written yet. The seismic record will write them, in the only language it knows. The work of the monitoring community is to read that language as quickly and as accurately as possible, and to translate it into terms that allow the people living in this valley, and the people responsible for their safety, to make informed decisions in the time that remains before the next chapter begins. Part 20, the final frame. We are now 72 hours into the diagnostic window that will determine how this swarm is remembered. Or we are approaching it. Or we are, in the most honest sense, somewhere inside a real-time observational experiment that will run to its conclusion regardless of what anyone thinks about it, says about it, or writes about it. The instruments do not care about our interpretations. The fault does not pause for our analysis. The window is running, and the data is accumulating, and the question that was open when this began remains open now in ways that matter. Let me return to where we began and walk through what has been established, because the discipline of returning to established facts is one of the few defences available against the twin temptations of premature alarm and premature reassurance. 2 criteria out of 3 have been met. The Brawley Seismic Zone has produced roughly 400 earthquakes in 48 hours at an accelerating rate that climbed from 22 to 33 events per hour. The magnitude ceiling has risen from sub 4.5 to 4.7 within a single 24-hour window, with both of the largest events occurring at brittle crust depths of 13 to 16 kilometers, the depth range where fault mechanics operate in the stick-slip regime that produces the kind of rupture sequences the monitoring community watches most carefully. These are not disputed facts. They are not interpretations or probabilistic inferences. They are in the seismic catalogue. They are real. 2 boxes are checked, and the physical significance of those 2 checked boxes is not trivial. An accelerating rate and a rising magnitude ceiling taken together represent a system that has not yet found its energy ceiling. A swarm that is decelerating and stabilizing tells one story. A swarm that is doing the opposite tells another. The third box, northward migration toward the Salton Sea and the southern San Andreas Fault, remains open. It is the test that the 72-hour window was defined to evaluate. It is the criterion that separates the routine interpretation from the alarming one, the criterion that distinguishes a Brawley zone doing what the Brawley zone has always done from a Brawley zone acting as a mechanical intermediary between the regional stress field and a fault segment that has been accumulating strain for 3 centuries. And as of now, the seismological data has not closed that question. The absence of a confirmed migration front is not the same as a confirmed absence of migration. That distinction is not semantic, it is the operational center of everything that follows. We know that the Coachella section of the San Andreas has been silent for 326 years, nearly a century longer than its mean recurrence interval, which itself is derived from paleoseismic trenching data that carries its own uncertainties, but points consistently toward a fault that ruptures on timescales of 100 to 200 years. We know it is a locked fault accumulating slip deficit at a rate of 20 to 35 millimeters per year, which over 326 years represents a stored displacement that must eventually be expressed as surface rupture. The arithmetic is not complicated. The physics does not permit the strain to accumulate indefinitely. We know it did not rupture in the 1857 Fort Tejon earthquake, which relieved stress along the Mojave and San Bernardino sections to the north but left the Coachella section loaded and waiting. We know the USGS places it among the highest probability major fault segments for a future large earthquake in the continental United States, and that assessment is not speculative. It is grounded in geodetic measurements, paleoseismic records, and the kind of probabilistic hazard analysis that has been refined over decades of observational science. None of that changes based on what happens in the Brawley zone in the next 24 hours. That hazard exists regardless of how this swarm resolves. It existed before this swarm began. It will exist after this swarm ends. What changes, what the 72-hour window actually resolves, is the narrower and more immediate question of whether the current swarm represents an active stress transfer event or a locally contained sequence. Those are different physical scenarios with different immediate implications, and the difference between them is not one of degree but of kind. A swarm that dies without migration is information. It tells us the corridor did not open this time, that the mechanical linkage between the Brawley zone and the southern San Andreas did not activate in a way that propagated stress northward, and that the sequence belongs in the long catalogue of Brawley zone episodes that were notable in the moment and unremarkable in retrospect. A swarm that migrates northward is different information, not proof of imminent catastrophe, not a deterministic trigger that guarantees a main shock on the Coachella section, but evidence that stress is propagating in the direction of a fault that is already well beyond its expected loading threshold. Those two outcomes are not equivalent. They demand different responses from the monitoring community, and different framings in any honest communication about what the data means. 3 scenarios remain on the table as this window continues running, and it is worth being precise about what each of them means and what each of them does not mean. The first is the quiet death, the most probable outcome, the least dramatic, and in some ways the most informative. The swarm peaks, the rate declines from 33 events per hour towards something more consistent with background levels. The magnitude ceiling stabilizes and then retreats, and the Brawley zone returns to its baseline seismicity over the course of days or weeks. This outcome would not mean that the Coachella section is safe, or that the hazard has been reduced, or that the 326-year loading clock has been reset. It would mean only that this particular episode did not become the mechanism of stress transfer. The hazard persists. The clock continues. The quiet death of a swarm is not a reprieve, it is an interval. The second scenario is stress without release, a subtler outcome that the public record rarely captures but that the scientific record must account for. The swarm ends, the seismicity declines, and the sequence appears to resolve. But the Coulomb stress redistribution produced by 400 events at brittle crustal depths has fractionally reloaded sections of the fault network that were already near their failure threshold. No immediate consequence is observable, no alarm is triggered. But the probability of future rupture on the southern San Andreas is marginally higher than it was before the swarm began, in a way that will be incorporated into the next generation of hazard models and will influence, in small but non-zero ways, the probabilistic assessments that inform building codes, emergency planning frameworks, and infrastructure investment decisions across Southern California, this is the scenario that produces no headlines and leaves the deepest fingerprints in the long record. The third is the foreshock pathway, the scenario that remains statistically unlikely at every moment of this window, and that nevertheless cannot be ruled out as long as the migration criterion remains unresolved. It is the scenario in which the current swarm is not the event, but the prelude to the event, in which the accelerating rate and rising magnitude ceiling are not the system's ceiling but its floor, in which the story that began with a cluster of 4.5 events in the southern Imperial Valley ends somewhere north of where it began, on a fault segment that has been waiting longer than the United States has existed as a country. There is an important concept in the philosophy of science called the difference between absence of evidence and evidence of absence, and it applies here with particular force. Right now we have absence of evidence for northward migration. The hypocenter relocations available from the current catalogue do not show a clear directional propagation front moving systematically toward the San Andreas. But absence of evidence is not the same as evidence that migration is not occurring or will not occur. Migration can be slow, it can be discontinuous, it can operate through stress transfer mechanisms that are not reflected in a neat spatial progression of hypocenters, but that nevertheless accomplish the mechanical work of loading an adjacent fault segment. The window is not closed. The test is still running. The data is still accumulating. Any statement about what this swarm is or is not that treats the open question as a closed one is doing something that science is not licensed to do. What I want to leave you with is not fear and not false comfort. Both of those are easy to deliver, and both of them would be dishonest in ways that matter. Fear without calibration produces paralysis and erodes the public trust that accurate hazard communication depends on. False comfort produces something worse, a population that has been told repeatedly that the alarm was unnecessary and that eventually stops listening to the alarms that are not. What I want to leave you with is the appropriate cognitive posture for living in a world where the ground beneath your feet is not the static, permanent foundation it appears to be. It is a dynamic system under stress, operating on timescales that dwarf human memory and human planning horizons, occasionally expressing that stress in ways that are catastrophic and swift, and doing so according to a physical logic that is comprehensible, even when it is not predictable. The southern San Andreas has been waiting for 326 years. Not patiently. There is no patience in geology. There is only stress and friction and the inevitable arithmetic of accumulated strain. It has simply been waiting in the way that all locked faults wait, by loading silently, storing energy in the elastic deformation of rock across a fault zone that may be 50 kilometers deep, building toward a moment that will arrive whether or not anyone is watching, whether or not the instruments are running, whether or not the monitoring networks have been funded and maintained and staffed by people who understand what the data means. The moment is indifferent to observation. The physics does not require a witness. We are watching. We have the instruments, the models, the monitoring networks, and the scientific frameworks to observe what is happening in real time and interpret it with reasonable accuracy. That is not nothing. That is in fact the result of decades of investment in the infrastructure of seismic science, the broadband seismometers, the GPS networks measuring crustal deformation at millimeter precision, the computational tools that can relocate hundreds of hypercenters in hours and produce a three-dimensional picture of where the crust is moving and how. We cannot predict the future of this system with the specificity that would allow us to say when and how large and exactly where. No one can. But we can observe it, characterize it, update our assessments as new data arrives, and communicate honestly about what the data says, and, with equal discipline, about what it does not say. That honesty is the obligation of the science. In 72 hours or something near it, this stops being an open question and becomes a case study. The Brawley Seismic Zone will have told us, in the only language it knows, the language of ground motion, fault slip and wave propagation, what this swarm was and what it was not. The answer will be added to the catalogue. The scientists will update their models. The hazard assessments will be revised by increments too small to make headlines and too important to ignore. The fault will continue doing what it has been doing for millions of years, indifferent to our timelines, unaware of our monitoring systems, operating according to the physics of stress and the geometry of crustal plates that have been in motion long before there was anyone around to give them names or measure their motion or build cities along their traces. And somewhere north of the Brawley Zone, in the crust beneath the Coachella Valley and the Salton Sea and the communities strung out along the fault trace, 326 years of accumulated strain are still waiting for the test that has not yet arrived. Still loading, still accumulating, still building toward the arithmetic resolution that the physics requires and that no monitoring network can prevent, only observe. Maybe this was it. Maybe this swarm was the stress transfer event that nudged the Coachella section fractionally closer to its threshold, and the threshold was not crossed this time, and the story ends quietly with a declining rate curve and a catalogue entry that future researchers will read and note and move past. Or maybe this was not it at all. Maybe the real test is still somewhere ahead of us, accumulating quietly in the dark, locked and indifferent, building toward the moment when the arithmetic finally resolves in the only way that physics permits, suddenly, completely, and without the courtesy of a warning that the instruments can distinguish in advance from all the other warnings that turned out to mean nothing. We will know more in 72 hours, but some questions take longer than that.